So previously I've told you that the displacement x is equal to the amplitude times sine omega t, and it's that sine function that gives us this shape of its position. Now you may have noticed that in the textbook or in the formula sheet it gives you the formula in this form using cosine instead of sine, and that really is because in most situations we have to start the oscillation at the amplitude rather than starting the oscillation here, so we end up with a cosine curve. Because in order to oscillate something you've got to displace it in the first place. If we don't displace it, it just sits there at the equilibrium position. So we displace it from the equilibrium position to a position which is now the amplitude, we let go of it and it will oscillate backwards and forwards. However, I have seen questions that talk about starting timing or starting observations from the equilibrium position, and so you just need to be careful. If the oscillations are starting from the amplitude, then use this one. Okay, so that's from the amplitude. Or if they are starting from the equilibrium position, use this one. Right, let's talk about energy then. So I want you to imagine a mass on a spring at the equilibrium position, and we stretch the spring so that there is a force and acceleration upwards. When we let go of it, it's going to oscillate from here. Assuming we say that down is positive, not that it really matters, then we've got positive displacement initially and we end up with that cosine curve. At that position though, the moment we let go of it, it's not moving. If I was to look at the kinetic energy at that point, then it would be zero. It's also zero here because that's the other amplitude where it temporarily stops. It's also zero here, and at the equilibrium position that's where it's moving fastest, so it's accelerating. It's no longer accelerating at the equilibrium position because the forces are in equilibrium, and then it starts to slow down or accelerate back towards the equilibrium position, and then so on and so on. So at the equilibrium position is where it's moving fastest, so that's where the maximum kinetic energy here and here and here and here. So we end up with a sine curve or a cosine curve depending on where we start from, with a frequency twice the frequency of the original oscillation, because for every period we end up with maximum, minimum, maximum, minimum. So we end up with two cycles of kinetic energy for every cycle of oscillation. Now if we look at the potential energy is maximum here, minimum here, maximum here. And so it does the opposite. When kinetic energy is maximum, potential energy is minimum, and vice versa. So we end up with a sine curve that does that. Now the total of those two added together will always be the same because we can't lose energy. Energy is conserved, and so we'll call this number here the total energy, which will go across the top. And we know that the total energy is equal to the kinetic energy plus the potential energy at any given point. Now at certain key points, the equilibrium position and the amplitude, then all of the energy will be one or other of those two. So there's the graph I just drew. Now let's look at how we can use that to derive some equations that might be useful. So I previously said total energy is the potential energy plus the kinetic energy, which means that at any given point the kinetic energy is going to be equal to the total minus the potential. Now the total energy, if we go back to our mass on a spring, the total energy will be equal to half kx squared, because that's the energy stored in a spring, and the further we extend it to start with, the more energy we put in the system. So the total energy and the maximum potential energy will be equal to that. So we can rewrite that and say Ek equals half k A squared, so total energy is when the x is the amplitude, minus the potential energy at any given point, which is a half kx squared. So x equals A when we first release it. We can simplify that, obviously, and we can also say that kinetic energy is a half mv squared. So we can say a half mv squared is equal to a half k brackets a squared minus x squared. Halves cancel, and therefore v squared equals k over m. Hang on, we've seen that before somewhere. A squared minus x squared. And previously we proved that omega squared for a mass on a spring was equal to k over m. So I can replace k over m with omega squared. So we get v equals omega, because I'm square rooting it all, square root of a squared minus x squared. Okay, so the velocity of the object at any given point is equal to that, and the maximum velocity is when the displacement is 0, so x is 0, and so the maximum velocity is omega a. If you were given a problem where you weren't given displacement information, you were given time information, of course you can go back and use assuming it starts at the equilibrium, or if we start the oscillation at the amplitude.